Welcome to the walking tutorial. We have 4 models and we will also do a 5th one, a simplification of the 4th one. So the first thing, when we walk, we want to go from A to B. One agent, one goal, let's walk there. And for that, we need to know a new command. It's towards. When you say towards and then turtle 0, so you say to turtle 1 towards turtle 0, then it will report the angle towards that turtle. Let's create 2 turtles to test it. Here is, and let's ask the turtles to set their x coordinate randomly. Or their y coordinate von mir aus auch. Yes. So this suits me better. You can, okay, turtle 0, I ask the turtle 0 towards turtle 1, and it says 175 because they're on opposite ends of the world, right? And they turn away from each other. If you believe me, then let's see what I got for you. I've got this person here. It's a turtle, actually. It's not a breeded turtle. It's just a turtle that looks like a person. And this is the patch that it wants to go to. And if I press here, then it moves, so it turns towards the goal. And then it moves 1 unit towards that goal. And then it also writes what distance is left until it reaches that goal. If it reaches the goal, meaning that the distance is 0, it will die in the next instance and it leaves a trail. How does that look in code? So here we need to define what goal the turtle has. So a goal is, in this case, always a patch. To set up the program, we clear everything and we create a number of turtles for which we have a slider. And all those turtles get their shape as person and are colored red and are distributed randomly in the world. And then we set this goal to one of the patches. And we tell that one patch, also in that case, the goal, to set its patch label. Every patch can have a patch label. Did you know that? So that's the small thing displayed on top, like a small string. So we set that to X in order to signify this is a goal. And after having done that, we finally tell the turtle we created to put the pen down so that we see where it's going. In the go procedure, we ask all turtles to elaborate or to find out the distance towards the goal. How much distance is there between me and the goal? And depending on that, we will do funky stuff. The turtle is in one of 3 states. Either it's walking towards the goal or either it's walking fast towards the goal or it's walking slow towards the goal or it's at the goal and dying at the moment. That's one of the 3 states, as you will see in a second. So we ask all turtles to find out the distance to their goal, and we make a local variable d that will store this distance. Also, we say that the turtle should set its label to this distance, but since the distance can be something with a comma, something with 17.4547, blah, 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 we just round it down, and this is the floor function. Yeah, so floor of 5.5 is 5. Yeah, there are other rounding functions like round 5.5, which would give 6, or ceiling, which would round up. Ceiling 5.5 is 6. Yeah, we'll learn a bit of NetLogo as we go through this example. So remember, floor, round, and ceiling all do rounding. The one rounds down, the other rounds up, and the third one, the rounds as we learned in school. So good. So I have looked at the distance between me and the goal. I've set my label to the distance rounded down. and I have set the patch underneath me to green. And now comes the funky stuff. When you have the distance, yeah, and when you're standing exactly on your goal, and you calculate the distance to that goal, to that patch on which you stand on, it can be through imprecisions in computer calculation that the distance is not exactly zero, but 0.0000, very small number. This actually happens. And so if we want to say, is your distance to the goal zero-ish, we have to say, if else D, or if it's not zero, we have to say, if D is greater than some small number, not zero, but smallish. Yeah. So there are two cases. The distance is still larger than zero-ish. Then comes this case. Or your distance is zero, then you die. So we have this case. So when the distance is zero, you die. Good. And when the distance is not zero, we have to walk. And the question is, do we walk fast or slow? But before we walk, we set our heading to the angle towards the goal. So it turns to the goal always. Now, if the distance is greater than 1, then we can walk fast. Yeah, we walk fast. And the distance is smaller than 1 or equal to 1, we walk exactly the distance left. Yeah. Good. So walking fast or walking slow. And now you get to appreciate maybe what happens more. So we set up this, we make a couple of more turtles, and they all have their goal, right? And now, since everybody has their goal, what will happen now? Everybody will see what the distance to the goal is. If it's greater than 0, then they make one step in the direction and then set their label to the distance left. So this is what happens. So this is what happens. And you will see that people whose distance is 0 die in the next step. So now everybody's after a while. So that was direct movement. Let's extend this terrible little program into a beautiful one. Because as you know, goals, there is not always only one goal. There are many goals. And for that, we need a new variable called goals. Today we learn walking. Shit. Oh no, that's good. It's recording. Sehr good. So let's again consider we now have a couple of agents and we say, and there is a couple of goals. So the patches are pre-selected as being goals. No, out of all patches, I grab a number of them, and this number is determined by num goals. So it's the same thing, but now turtles walk to the first goal, then to the second, and then to the third before they all die. Yeah? So this is the case with multiple goals. And how many goals is the variable num goals? So in addition, I marked everything that is new with new. Yeah. So I had this goal where I'm headed to. And now I have a second variable called goals. The concept is this. At the beginning, goals will be filled with all the goals I need to visit. And goal remains empty. When goal is empty in the go procedure, when goal is nothing, then it will pick the next goal from the goals, if that is possible. If not, it will die. But if that is possible, it will pick the next goal out of goals, shorten goals, so that what it picked out is left out. And then it will again walk towards the goal. And if it has reached the goal, then goal will be set to nothing, meaning nobody. And then it will again repeat the step. Is there something still in goals? Pick it, and so on. Let's go through the code in detail. So in setup, what has changed is that I'm now getting a couple of patches depending on your slider. What I do really is I execute this thing, n of num goes patches. Let's see what this does. N of num goes patches. It gives you 3 patches. Yeah, I can write also as a number. N of picks out of a set of things like agents or patches. It picks the number you give. So you see at random. So patches is the whole set, and I say 5 of them pick out. Yeah, is that clear? N of random, completely random, and it will pick every time something different. It's randomized. So here I have a local variable called goals agent set, because this is a set. Yeah, it's unordered, and as you would expect in a set, yeah, every time you access that set by the use of ask, you get a different order. So anyway, so I'm storing the 3 goals every turtle has in a variable called goals agent set, and then I'm saying ask those things, ask those patches, please, to set their patch label to X. This is nothing new like before, so we know it's a goal. And then to convert an agent set or a set, something unordered, to an ordered list, because for goals, we would like a list of things that are in succession, yeah, not randomized. In order, we have to employ a trick. Everything in the agent set is a agent or is a patch in that case. And if I make self of something, I get a list of that. I want to show you this with patches, so it's less of a hassle. If I put this in self of patches, then I get a list. Out of all patches, it picked at random every patch, and the patch told his identity. Patch something, patch something. Now it's a list. As you see, this is a list. So I have turned the set into a list, and I'm storing this in a local variable called goals list. And I'm setting now the agent's goals to be this goals list, and I'm setting the goal of that agent to be nothing or nobody. And as last step, this is not new, I tell the agent to put its pen down so that we can better get a look at it. All those examples are uploaded to Tuvel, and you can download them from there. Also, for the video people here, because I'm recording, those examples are also on GitHub. I will put in the comment text where it is. So in Go, I now ask the turtles to, and this is new, to see whether it has, if the goal is set. If the goal is not set, then we need to pick a next goal. And this again depends on, do we still have next goals? This is the empty command. The empty command looks into a list and sees whether that list is empty. In that case, it returns true. So if the goals thing has no more goals inside because it's empty, then we ask the agent to humbly die. In all other cases, there is still something in goals, and I'm getting the first thing there is from goals. And I'm setting goals to be the first thing in goals. Set goal, first goals. But now the list goals is still as big. I have to shorten it by 1. And how do I shorten it? I have to omit the first thing from goals. And for that, there is this handy little command, but first. So I say, but first goals, and this gives me the goals list shortened so that the first thing is omitted. So I'm setting the goals to whatever comes out when I say, but first goals. To give you a more practical or a more understandable example, let's do the but first. Here is a list, 1, 2, 3, 4. And when we say but first 1, 2, 3, 4, then 2, 3, 4 comes out. Yeah. There is also a but last. You can imagine what happens. Good. I have put the first thing in goals into the agent's variable goal, and I've shortened the goals by 1, and that's cool. So the rest doesn't apply. When we run this again, this agent has a goal set. So the goal is not nobody. Yeah. When we execute go the next time for this agent, the goal is not nobody. Then it does everything again what we did already. It turns towards the goal. It gets the distance to the goal. It sets its label to that distance. It makes the patch color of the underlying patch green. If the distance is larger than 0-ish, then it turns towards the goal. It walks. If the distance is greater than 1, it walks 1 forward, or else it walks the remaining distance to the goal forward. So now the question is, where does this apply? When the distance is 0, there is something new. When I'm exactly where I should be, standing on the goal, I set the goal to nobody. Why? Because when the next time go runs, I'm coming into this again. The goal is nobody. I'm looking, is there still goals we can get something from? If not, die. If there are, set the goal. Yeah? You notice the beauty of this code. It does things in more or less three different states. Good. And now we reappreciate this walking. So next thing, don't walk over the lawn. We want to restrict the walking to places, or the goals to places where we want them to be. And I think this is already manageable for you. I'm importing a map. The map is here. Yeah, this is how the map looks. I'm importing this map, and now the goals shall only be on the street, on the black thing. So we say, how do we filter patches so that we get only those ones that are on the street? Patches with, what's the color? Patch color equals black, right? So instead of the old thing, yeah. The only thing that really changes is we take patches with patch color is black. That's now how we select. Previously, we said n of num goals patches. Now what we added is with p color is black. Yeah. So and the rest, yeah, good. Importing a map is also clear. Import p colors, and every color that isn't white, because you could have scaling artifacts. Yeah. So because of scaling, you get something that is not completely black. Yeah. So we say everything that is white is for sure not meant as a street, and everything else is a street. That's why we say ask patches with patch color is not white to set its patch color to black immediately. Yeah. So we have converted it into truly black and white. And the rest of the code is the same. So go. Now, see, this is bad. It should walk along the street, ne? We thought it would do that, but it doesn't. Cannot. It walks directly, turns toward the goal and walks directly. We don't want that. How to do that? Now the fourth walking program, and then we will try to put this walking program, simplify the walking program a bit. Yeah? Simplify, simplify, simplify. Okay, we import the map again. And what we also do is we make this look like a typical village in Lower Austria by putting houses next to the street. That's the village. And the number of houses is given by this slider here. So I'm selecting patches that are white and are next to a black patch. Who wants to test their, how do I address those patches? Ask patches with, what are those patches that are beneath the street? What color do they have? Yeah, white. With color is white. And now comes the second criterion. And any neighbors with patch color equals black. Looks complicated, is not. Is not complicated. White patches that are next to, meaning neighbors. I could also write with any patches with P color is black in radius so and so. But this neighbors is really handy. Yeah. So those are the 8 neighbors. I could also write neighbors 4. What do I tell them? Set your patch color to yellow. So those are the candidate patches. Yeah. And now out of those, you select so and so many according to num houses patches to build a house on. What command do you use? N off. N off, remember? N off those patches. Yeah? Okay. So, and now, what else do we do? We put the houses there, and also we put on every patch that is black, we put something like this. Here, a dot. And then, what is this? This is a waypoint. A waypoint. Waypoints are small dots that are connected by links, and along this can the turtles march. And what we will find out, so on every black patch, in every middle of a black patch, I put a waypoint and I connect it to all the waypoints in the surrounding. So in radius 1, for example, or on the neighbors. Yeah. Then I have a graph. And the nice thing is, these things here, these houses, these are also waypoints, but they have a different shape. Yeah. And what you also see is that those houses are connected to the waypoints that are on the roads. Yeah. So the concept is an agent is born in the graph. Also it's born on a waypoint and wants to go to somewhere that is a waypoint. And in order to do that, it uses a library. The library is called, or the plugin, or the extension, as we say in NetLogo, is called network. And you can ask this library to say, I'm here, I want to go there, and it will tell you exactly which waypoints you need to visit in between. This is the beauty, and it's called the Dijkstra shortest path algorithm, which we will do after this video is finished. I will show you exactly how this works technically. But for the moment, let's just consider there is a library that can do the shortest path between 2 waypoints in this graph. And this things connected, waypoints connected by links is our way graph. Yeah? Now, if we do that, we get the following. Aha. That's too fast. Let's do it again. Slower. So we look at the road. Here you see the waypoints as they build themselves up and connect to the surrounding neighbors. Then come the houses, waypoints, which are connected to the nearest waypoint on the street. And then you see those agents marching on this graph, yeah, from house to house. And as they march, we increase the P color of the street a bit in order to show you a bit of density. Yeah, this is how Google works. If you go to Maps, it is exactly the same what they do. You start at a node, you want to go to another node, and in between is the shortest path search, only a bit more sophisticated. So let's look at the code because the code never lies. We have to, at the top, we have to say extensions NW for network. This is new. So this will import our network extension, which we can then ask for the shortest path. Then, since there are now two things in our simulation, namely the persons that move and the waypoints that represent where they can move, we have to now introduce a breed for each of those. So previously we had only turtles. Now we have two types of turtles. We have the waypoints and we have the persons. And then instead of turtles own, we then say persons own. So they still have their goals and still have a current goal, but the goals are what? Patches. Are they? Let me just say. No, the goals are waypoints this time. Houses, always houses. So they go to a number of houses. They start at the house and then they go to a number of other houses. So in goals, we have waypoints. In goal, we have the next house to go to. But how to go to that house, we have to have a new variable, intermediate points. So my current goal is, I don't know, the institute library or whatever. But in order to get there, I have some intermediate crossings I have to sort of go through. Yeah. So I have sort of three levels of abstraction. So what happened here? So let's go through the code then. First, we clear everything, then we import the map. And everything that is not white is probably a street. So we say your color is black, regardless if you're a little bit more black or less black. And then there is this sprout. Sprout is a patch command, and it creates in the middle of the patch a turtle. And if you say sprout waypoints, it doesn't create a turtle, but specifically a waypoint turtle. Yeah, a turtle with a breed of waypoints. So you ask the black patches to grow a turtle in its middle, one, and that turtle should be of breed waypoints. And we have two different types of waypoints, waypoints that stand on the street and waypoints that are houses. So in this time, we stand on a street because underneath us is black. And we set the shape of that waypoint to a small dot. The dot is defined in the NetLogo turtle shapes library. Here you can see that's a dot, as opposed to a circle, which is the larger version of the dot. Yeah? Good. And we set the color to gray so as to signify this is a waypoint. And then imagine how this happens. We saw how this happens. So slowly it picks black patches and creates waypoints there. Sometimes there are other waypoints surrounding that one waypoint which is created now and sometimes not. Doesn't matter. Whoever is next to me, I'm creating a link to that one. Create links with other waypoints to every other waypoint there is in a radius 1. And then it happens that you get this nice graph, yeah, fully connected to its neighbors. So now I'm asking now the patches that are white and next to the street, yeah, P color is white, and any neighbors 4, in this case, only the north, east, south, and west is checked with color is black. This is exactly what we had as candidates. We marked those in yellow. Yeah, and I'm asking not all of those, but n of those, namely whatever you had in the slider. Yeah, so many patches I will ask randomly to what? Also make a waypoint there, but give it the shape of house and set its color to green because these are the houses. And say, remember who you are, and then say, create a link with the nearest street waypoint. So this is waypoints with the shape of dot. And here's a new command. With min, there could be multiple. There are multiple of those, but I want the one or those ones with the minimum what? Distance to myself. Yeah. If you have to the east a waypoint and to the west a waypoint, and they are exactly 1 unit distance, you have two nearest ones. Remember this. And because this can be, I'm picking at random one of those waypoints that are nearest. So I have to put here one of. Yeah. One of selects one in a set. Yeah, at random. This is how I do the accesses to the houses. So I connect the house to the rest of the way system. Now I've got the way graph. And then I'm creating the persons as I created the turtles previously. So instead of create turtles, I say create persons. So it puts the breed of person. And I pick one of the waypoints with the shape of house to be the home of that turtle. And I'm setting the coordinates to the coordinate of that home, the X and the Y. So I'm putting the turtle there. And then I pick a number of house-shaped waypoints that are not my home. Yeah, waypoints with shape is house and self is not my home. And I pick n of those, depending on the amount of goals you want. And I'm calling it the goals agent set. Everything else didn't change. So this is the things which we have to visit and so on. Now, the last thing in setup, I tell the network library to restrict its shortest path search to the following things. To the waypoints. Only waypoints are valid nodes. So in graph theory, we speak of nodes and edges. Yeah, the bubbles, the round things that are connected with links. Yeah, the one is the node and the other one is the edge. So it searches along the links that connect waypoints, and it will not try to search for the shortest path using persons. Yeah, you can connect a person to the road graph and it will not eat it. The algorithm will not go try to search along a person. Yeah, you're just telling it, restrict yourself to waypoints when you search, and the waypoints are connected via links. Okay, so not that important because persons aren't connected to the way system, so it wouldn't find anything anyway. In Go, we now don't ask turtles, we ask persons. And we have the same thing as previously. If the goal is not set, we see, is there other goals? Yes, there is, or else we die. And then we set the goal to the first item in goals, and we set the goals to be one less. Yeah? Okay, this is what we did. But now comes the new thing. Yeah, that's nice that I have now worked out. I need to go to the other end of the village to that other house. But how do I do that? Now comes the important point. I'm standing here. So I'm standing here. Here is a waypoint. I know that I have a waypoint under my feet. So I can say, let's start, which is a variable, be one of the waypoints here. What does something turtles here do? It looks at the patch on which I stand It gives me the set of turtles that stand on the same patch. Yeah? So waypoints here filters this by the breed. So waypoints here is the patches, the waypoints that are on this patch. Good enough. And the destination is, of course, the goal. Yeah? And now I ask the network library to do its job. NW double point. So I'm calling the extension, network extension, please. Tell me the purpose on the path to the destination if I am the start. You have to write this way. This gives you, yes, you have to go there, a list. This gives you the list of intermediate points. Good. Now that we have this, we can set the intermediate points to that list. And now we have set the goal, intermediate points is filled. Okay. Now, when we come back in the next iteration of Go, we have set goal to something, but we actually, goal is like high level, but what's the low level? What's the next intermediate goal? Now let's find out. So let the next intermediate point be the first thing in the list, intermediate points. And then we do the distance to that thing. And if the distance is not 0, we set that heading towards that next intermediate point. And we make a big or small step, it doesn't matter. And also as we walk, we say, okay, if the ground beneath you is something like the street, so the color is, smaller than gray, and gray is 5, I guess, then we make it a bit lighter so as to signify a density. Yeah, this is only for visualization. Forget that. So this is not important. The important thing is we have determined the next intermediate point. Let's assume that would be in the door. Yeah, I'm walking towards it, and at some point I'm reaching that. Then the distance is 0 or nearly 0. Yeah. Okay. Then I simply leave that intermediate point away from the list. Yeah. Set intermediate points, but first intermediate points. So I leave that away. And now I ask, is it empty, the list? If it's empty, yeah, then I have a problem. If it's not empty, I will continue the same procedure, go to the next intermediate point and reach it. Yeah. Only if it's empty, I do the following. I set the goal to nothing, so it will try to grab the next goal. And now we have it. So come on. Dum, dum. This is great. Could put some cows somewhere to make it more realistic for Lower Austria. Good. Let's go. That one. No, that one. Come on. Okay, another one. Ride one of persons. Yeah, riding person, somebody. And now we go. So that's actually not working so well in 3D. Because seems to be a shift here, né? Things are shifting. Ah, that person is dead, so we can't write him. Can we follow? Well, maybe we can follow in the next iteration instead of writing. These are all new commands. Yeah, you're right. So, slower. Follow one of persons. That also doesn't work so well, does it? Oh yeah, that works better-ish. No, no, it doesn't work. Anyway, this works. Fair enough. So you see, they are all moving along our street network. And now we want to simplify this code. Hmm? Do we need goals? Do we need intermediate points? Do we need goal? How can we do that? Okay, let's simplify. Yeah? If you had thought, when you have determined a couple of houses to be the goals, you could uh, instead of finding out during Go what the intermediate points are to that house, you could have done that in setup. So we could very well have when when we got those three houses which we need to visit, we could have looped through that and then immediately say what are the other waypoints I need to visit in between. This would we could have done. Also, shall we, or are you overwhelmed? I think you're a bit overwhelmed. Okay, the next thing only as okay, we are not simplifying. It's okay. The other thing which is beautiful is this um, thing uses intermediate points and not intermediate point. So it always uses the first one in intermediate point as the thing where it's steering to currently. So we could have saved ourselves some effort by simply not defining goal. Yeah, could have skipped that. We could have simply said the first one in goals instead of goal. Yeah, that would be easy. Yeah, and so on. Anyway, let's leave it at that. Okay, how do I Freigabe stoppen? Beenden.